We introduced electrochemistry yesterday, and hopefully at this point you feel very comfortable balancing redox reactions. Remember, with electrochemistry, you're dealing with electricity, flow of electrons, so with the transfer of electrons from the substance that's being oxidized to the substance being reduced, you will understand how redox is going to lead into electrochemistry. Voltaic cells are those in which the electric current is generated from a thermodynamically favorable redox reaction. So you're going to use that factor to essentially serve as your electrical source. And we'll talk about what happens when you don't have a thermodynamically favorable reaction toward the end of the unit. We mentioned yesterday the different components, and rather than just walking through this with you, I showed you 1 1/4 videos, and you saw this very relaxing video. I just want to point out a few things to you, or have you point them out to me, so that I know you're comfortable with it. For example, this is called starts with an E. Electrode, as is this. This upside down U-shaped tube is a salt bridge. That permits ion migration. We're going to talk about that a little bit more. Here is the wire, and what flows through the wire? Electrons. Now, which substance loses electrons? The ones that gets oxidized or reduced? Oxidized. So electrons will flow from the substance that gets oxidized to the substance that gets reduced. And we watched this entire video yesterday, right?
Yes.
Okay. This thing was driving me nuts, so I turned it off. Now I gotta turn it back on. Tippies. Love this toy.
Is a zinc bar placed into a zinc sulfate solution.
The other thing I want to mention is that the anode is where oxidation occurs. An-ox. Reduction is where is going to occur at the cathode. Red cat. Electrons flow from the anode to the cathode. Now, an electrode is a metal strip, so it is an uncharged species, if you will. And this video is the second one in your notes, and if you want to go back and look at it, I would recommend it. It really explains some key things. This video is much longer. I would recommend it in its entirety. There are a few things I want to point out here.
In this video, we're going to talk about galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation reduction reaction. But we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic cell, one that you can actually make in your own. So here's what they are. First, we start with beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with it.
So what electrode do you think will go in the zinc sulfate solution? for example, in the zinc sulfate solution, I'll put a zinc electrode. What electrode will go in the copper 2 sulfate solution?
Copper?
Okay.
Oh,
You got these two solutions.
yeah.
We take a piece of zinc metal.
So there's your zinc, and then the
two
copper.
pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we can actually do is we can take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solutions. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2 plus ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and the zinc atoms in the piece of zinc. Then over here, we have these Cu2 plus.
So this is the same type of thing.
Cu2 plus has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons.
And we're going to talk
So
about
in
why.
this tug of war, Cu2 plus ends up winning. Let me show you how this happens. So Cu2 plus really wants electrons.
In
So
reverse.
it's kind of like it calls over here to zinc, which has a weaker pull on the electrons. It says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens? Gives away 2 of its electrons.
And where did those
These
electrons go?
Enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change.
Now, if zinc gives away 2 electrons, it's losing 2 electrons. So zinc is being oxidized, and oxidation occurs at the anode. So this is the anode, and this is the cathode.
It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2 plus. Now, changing from neutral zinc to zinc 2 plus has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water.
So as that ion essentially comes off the electrode, if you will, what happens to the mass of the electrode? It's going to decrease because the metal is converted to the ion. Well, as these electrons move through, they react, if you will, with the copper 2 plus to make copper. So at the cathode, what happens to the mass of the electrode? Okay.
So after this zinc atom turns into Zn2 plus because it lost these electrons, it's no longer part of the solid
that's what I illustrated to you.
Neutral
And this guy's now gonna
which
attach
means that
to.
it is no-
Like I said, it's a very long video, so I can't show all of it to you, although it might be worth
those
looking at.
Cu2 plus
You can
ions
see the
are
loss,
coming
you can
out
see
of
the gain.
solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these two pieces of metal actually change size and shape. Here's some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms.
You're going to do the lab, you're
loses
gonna measure
electrons.
voltage.
So that means that oxidation is happening on this side of voltaic cell. And over here, this Cu2 plus ion is gaining 2 electrons to turn into a neutral copper atom.
So that's
So
reduction.
reduction or gain is happening. So the piece of zinc
So reduction at the
is going
cathode,
to be
oxidation
the
at the
anode.
anode. And these are the two equations showing oxidation and reduction. The sum of the two equations, once the number of electrons is the same, is your redox reaction. The other thing I want to just show you is the cell notation, as well as, I can walk you through the cell notation if it's easier, and then the salt bridge.
We're often asked to represent them in cell notation, which is a shorthand abbreviation of the chemical reactions in the voltaic cell. It's a way that we can show what's going on without drawing a picture of the whole thing, okay? Cell notation is sometimes referred to as a cell diagram, just so you know. So here's how we would write what's going on in this voltaic cell using cell notation. We start on the left with the oxidation process, okay? How does the oxidation process start? Well, I have the half reaction up here. It starts with solid zinc, okay? So I will write Zn solid right here. That's how the oxidation begins. Then I put this line here, and I show what we end up with in the oxidation process, which is Zn2+, okay? So Zn2+, and that is dissolved in water. It's part of the solution. It's aqueous. So this shows the oxidation process that happens in the half cell over here. Okay? Then I put 2 lines like this, and these 2 lines represent the physical boundary between these 2 half cells, or you can think of them representing the.
And how do you think the rest of it would be represented? If this went zinc slash zinc 2 plus, then you'd have Cu2 plus slash Cu. Yep. And then here comes the salt bridge component.
The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean.
So in the salt bridge, you're going to put a highly soluble salt, such as we use potassium nitrate in our lab. He's going to use sodium chloride. The only problem with sodium chloride is if you have silver ion in there, you're going to get a precipitate. So a salt bridge will go here, and it allows ion migration. It prevents buildup of charge. For example, over here, this is where zinc was making zinc 2 plus. So you're getting more and more zinc 2 plus. So to counteract that positive charge, you're going to have the negative ions in the salt bridge migrate toward this area to neutralize this. Here what's going to happen is the copper 2 plus is generating copper, so you're going to have a buildup of negative charge, so you're going to introduce positive charge from the salt bridge, and that's what he's going to show you here.
The two solutions are made up of both positive ions and negative ions. I didn't show these zinc atoms are going to give electrons, lose their charge by gaining electrons and turn into neutrally
So
charged
here you have positive charge
copper.
buildup.
Now,
Here
there
negative.
are a whole lot more SO42 minuses than there are Cu2 pluses. So a negative charge begins to build up on this side. And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that, in our case, is filled with sodium chloride. You can see the Na plus and the Cl minus ions. Now, at the ends of the salt bridge, there are cotton plugs, a little bit of cotton, and the cotton prevents the solution from just pouring out into the half cells. But these ions are able to slowly pass through the cotton plugs.
So which ion will go toward the sulfate buildup? The sodium ion, and the chloride ion is needed here to neutralize some of that positive charge.
And here's what happens. Oh, from being able to work. Wow, so we just learned so much about galvanic.
All right, so there are your voltaic cells. That just gives you a brief introduction. And again, I would take the time to walk through. He walks through it very well. Everything he said is in here. We're going to use voltmeters. These are electric meters that actually measure the difference in electrical potential between 2 points in an electrical circuit. We'll talk more about that and go over some voltmeter type readings in just a bit. Here's a galvanic cell. Instead of the U-shaped ion, U-shaped salt bridge, it has a porous disc which basically serves the same function. We'll be using not U-shaped tubes but filter paper that are dipped in a soluble salt solution. There are many, many types of common voltaic cells, batteries that you use daily. You've got dry cells, alkaline batteries, that's what's in your calculators. The nickel-cadmium batteries are a little bit newer. They are rechargeable, so they work well. Lead acid, some types of lithium battery. What's in your cell phones? There you go. And those videos are right here in your notes. The first one is the DeWitt, the very long one, and the second one is the very relaxing one, but they're both quite good. The anode, again, is where oxidation occurs, anox. This is the source of electrons, because if something's being oxidized, it's losing electrons, and those electrons flow through the wires to the cathode where the reduction occurs. At the cathode, the electrons are received and the reduction occurs. It's cations and anions that carry electric charge through solutions, and we're going to do measurements in volts. And a 1 volt is essentially a joule per coulomb. We'll get into that unit a little bit later on. The driving force that actually propels electrons from the anode to the cathode is known as the cell potential, abbreviated E cell. That's what we're going to be measuring. He talked about those cell diagrams. I think you're good there. Sometimes you use an inert electrode. So if, for example, you don't want to generate solid, you're not going to use an electrode that will allow for the buildup or loss thereof. So if you have a reaction in which you have 2 ions, you can still see that this is the loss of an electron, oxidation. You're going to use an inert electrode such as platinum. Same thing if you have a gas you can't make solid chlorine. So you're going to use platinum as an electrode. And the one new piece that we want to focus on today is how to calculate standard cell potentials. You'll see that substances can gain or lose electrons, and their ability to gain electrons is going to essentially be their standard electrode potential measurement.
Is it possible to have a part 2 question where you have to explain how like the salt bridge works or how the
They may ask you what ion flows to the oxidation reaction, what flows. They may ask you the function of the salt bridge. They may ask you what would happen if you didn't have a salt bridge. and your voltage would immediately decrease to 0 and stay there. And we'll talk about that when we do the lab as well, but that's a good question. We've got a reference point, a 0 point of electrode potentials. This is a standard hydrogen electrode. What you're showing here is the reduction ability of proton to generate hydrogen gas at 1 atmosphere of pressure. You would need a platinum electrode, and that is a value that is immediately set at 0. Other substances have standard electrode potentials, and that's based on the tendency for reduction to occur, and you're going up against hydrogen. Under standard conditions, concentration of a solution will be 1 molar. If you have a gas, it's going to be 1 atmosphere of pressure. And to establish these standard electrode potentials for all other half reactions, they're going to be based against the standard hydrogen electrode. Those values will be supplied to you prior to 2014. Standard reduction potentials in aqueous solutions at 25 degrees Celsius were provided to you. Here's the 0 reference point, and what you're going to see is that any substance above proton is more likely to be reduced than proton, hence the positive E values, positive standard reduction potentials. Any substance below is less likely to be reduced than proton. The substance most likely to be reduced off this table would be fluorine gas. The substance most likely to be oxidized is lithium. And your insight before was excellent, because the substance with the greatest activity of metals is lithium. And that's the substance that's most likely to be oxidized. Lithium ion has the lowest standard reduction potential. So when you're above proton, that substance is more likely to be reduced than proton. They don't give you this whole big chart, they just give you what you need. And on your practice exam that you're doing over spring break, I picked the one that had the least electrochemistry, because this will be 1 year that we don't get electrochemistry done prior to spring break. So I wanted to make sure that the exam I picked was one that you had the greatest success rate on. It had the least part 2 aspect of it. That was last year. In 2014 and 2015, there was a huge question on electrochem, and once we get through, you'll be fine with it. To calculate the standard cell potential, not just for a half cell, what you're going to do is you are going to subtract the standard reduction potential of the anode from the standard reduction potential of the cathode. In your book for homework problems, that table can be found on page 829. I already indicated that the substances most likely to be reduced have positive E cells above. To calculate it, let's take a look, and I want to point out several things here so you can be successful. Go ahead, Austin.
Does the number tell you how effective the voltaic cell will be? Is that what it is, like the effectiveness?
I don't think so. Any voltaic cell has to have an E cell that's positive. And that's because for a voltaic cell, delta G has to be negative for thermodynamic favorability. That's what provides the driving force. If there are greater degrees of them, I don't think so. Don't think so.
So as long as it's more likely to get reduced than oxidized, you're fine?
Let me answer your question in a minute, because I think I know where it's going. in regard to the example shown, it says calculate the standard cell potential for the following voltaic cell. And I also just want to indicate what would be provided to you here because it may not be clear. If they just gave you what's listed in the example, and that's not all they could give you nowadays, you know from that example, based on the way the cell diagram is indicated, that notation, that zinc is being converted to zinc 2+, and that copper 2+ is being converted to copper. That you can derive from what's given alone. This has to be the oxidation because you need a balance of charge. This has to be the reduction. Reduction occurs at the cathode or the anode? Cathode. Oxidation occurs at the anode. So this information you could derive, and if you were asked to write a net equation, you could do that. Zinc plus copper 2+ yields zinc 2+ plus copper. The other information that would have to be given, and I didn't write that clearly, so I want to make sure it's clear, is they will give you reduction potentials. They'll give you some type of table. For example, they'll give you copper 2+ plus 2 electrons yields copper, and that will have an E value that is a standard reduction potential of 0.340 volts, and they'd have to give you the zinc reduction potential, even though zinc gets oxidized in your example, of the following. So this would be given. From what you did previously, you know that zinc is being oxidized and copper 2 ions being reduced. And E cell is equal to cathode minus anode, and this little naught sign means under standard conditions, 1 atmosphere of pressure, 1 molar for an aqueous solution. So all you have to do now, you don't have to change signs, you don't have to multiply anything. This is an intrinsic property. It's very, very easy. What's given is what you use. Figure out what the cathode is. That's going to be this one. And you have 1.103 volts. Now, in regard to the degree of, for a voltaic cell, E cell must be positive. So if they didn't give you the overall reaction, you still could figure it out because only one combination here is going to give you a positive E cell. Okay? Two other examples, and I think we'll call it a quarter. Critically important. It says calculate the standard cell potential for the following reaction. They give you silver ion, they give you nickel, they give you silver, they give you nickel 2+, and you do need to balance that little guy for charge. The other information that's given in your notes, you don't need to recopy. I'm just trying to make the problem complete on my sheet. As follows. So all of that was given. Now again, the equation is given here. I did need a 2 here to balance off the electrons, but I do not ever, ever multiply an E by 2. And even though I can clearly see that the nickel reaction is in reverse because nickel is being oxidized, I do not flip the sign if I want to calculate E cell as the cathode minus the anode. Now, different books do it differently. Do whatever you want. Do it right. So what you're going to have here now is you know that the silver ion is being reduced. Reduction occurs at the cathode or the anode? Cathode. Oxidation at the anode. So the cathode 0.80 volt minus negative, and that's 1.05 volts. And again, E cell must be positive for a voltaic cell. So if they didn't give you the equation, you could figure out what it was because you know only one combination is going to give you a positive E cell.
So if we come up with a negative number, we messed up.
In a voltaic cell, correct. It'll all change for the electrolytics. All right, the last problem that's indicated here is one in which I give you the overall E cell and you have to figure out the reduction half reaction. Give it a shot. Try. Last big brain tease before break. Give it a shot, give it a shot.
Dr. Kalish,
Yes.
in a voltaic cell, so you could oxidize the anode without having like the equivalent ion in the solution, but you can't do the same thing with the reduction, right? Do you know what I'm
You
saying?
can.
You can? You can do the reduction part without having...
You mean with an inert electrode? You can.
Oh, you can.
Yeah. What'd you get? What'd you get? I was just teasing. Sorry. I was marking my notes where we're coming back after break. Green for go? Nah, that won't remain. I won't remember that. Here's my note. I'll remember. What'd you get? What'd you get? That's what I got. I just did sig figs. Is that what you got? Electrochemistry is actually very, very simple, and you're good at balancing redox reactions. They went weak on it last year. They may go stronger on it this year. Just sometimes the questions are a little weird. When we get back from break, we will link this particular topic with thermodynamics. From there, we will link it to equilibrium, and then we'll get into the electrolytic cells, and we should be able to work through that when we get back on Monday and the block day, and we'll have a lab to do, and then we will start reviewing like crazy. Please don't forget that your spring break assignment for period 7 is due on Wednesday. The lab will be due on Friday, in the lab tab on Edline, in the data table, they have hints on how to do the lab. In the lab tab, there is an Excel spreadsheet where if you type your absorbances in, you can generate a calibration curve and then you can read yours off the graph.
Is there gonna be
Hang on one sec. Questions here? Okay, so that'll leave us in Electrochem dead middle, and we'll pick up after